The spheres, which are about the size of cities, seem small, quiet, and easy to forget. Magnetars, on the other hand, are not safe. These are the most magnetized things in the world. Their fields are so strong that they can separate electrons from atoms, bend light, and give off more energy in a single flare than the sun does in 100,000 years. They are born when huge stars die and bend the rules of physics until they break. If one ever let out all of its anger near Earth, we might not be around to tell the tale. Birth in chaos: how magnetars form. Every magnetar starts out as a disaster. It starts with a huge star, something 8 to 20 times bigger than our Sun. It burns brightly and quickly, turning hydrogen into helium and carbon, and it keeps moving through the periodic table until it reaches iron. Nuclear fusion stops when it gets to iron. The star's core can no longer be used to get energy. Gravity wins. In a split second, the core falls apart under its own weight with unthinkable force, packing more mass than the Sun into a sphere that is only 20 kilometers across. Neutron stars are made this way. A neutron star is a city-sized object that is so dense that a teaspoon weighs as much as a mountain. But magnetars are the rarest, most extreme members of this neutron star family. Only about 1 in 10 neutron stars becomes a magnetar, suggesting something unusual happens during birth. Ordinary neutron stars spin rapidly and carry strong magnetic fields, but magnetars require conditions far beyond the norm. Magnetic fields up to 10-15 Gauss, trillions of times stronger than Earth's, strong enough to tear atoms apart and rival energy densities found nowhere else in the universe. The question is, how does a collapsing star make a magnetic monster instead of a normal neutron star or a black hole? Astrophysicists suspect 2 key ingredients. Rapid rotation and dynamo amplification transform some newborn neutron stars into magnetars. During core collapse, conservation of angular momentum spins the shrinking core faster and faster, like an ice skater pulling in their arms. If the core spins in less than a few milliseconds per rotation, differential motion between layers combined with turbulent convection may ignite a dynamo effect, similar in principle to how Earth's liquid outer core generates our planet's magnetic field. But here, the scale dwarfs anything we know. Nuclear density matter rotating hundreds of times per second, temperatures exceeding 1 trillion degrees, and turbulence on kilometer scales all conspire to amplify magnetic seed fields to colossal strengths. Within seconds, a magnetic leviathan is born. Observations indirectly back up this idea. Magnetars like heavy progenitors, stars that are heavy enough to make cores that spin quickly and are compact before losing angular momentum through winds or interactions between binary systems. Some of them live in groups of young, huge stars, which suggests that their ancestors didn't last long before exploding in supernovae or even hypernovae, which are the most powerful explosions of stars ever seen. GRBs are another sign that something is wrong. These are the brightest blasts in the universe. Some of them only last seconds, but they can light up whole galaxies. Some models connect long-lasting GRBs to proto-magnetars that spin very quickly. The energy from the proto-magnetar's rotation is turned into magnetic energy and relativistic winds, which power the strong gamma-ray emission before the new magnetar slows down or falls even more into a black hole. In this view, magnetars are not just the remains of stars that have died. They may also be the cause of some of the most amazing events in the history of the universe for a short time. The supernova itself may also carry magnetar fingerprints. When astronomers observe superluminous supernova, explosions 10 to 100 times brighter than typical core collapse events, magnetar engines often appear in theoretical models. As the newborn magnetar spins down, losing rotational energy through magnetic braking, it injects energy back into the expanding supernova ejector, keeping it hotter and brighter for weeks or months longer than radioactivity alone could explain. Several superluminous supernova light curves match this magnetar-powered scenario, suggesting we've already seen magnetars announced at birth across cosmic distances. The birth of a magnetar is violent and still not fully understood. In less than a second, the collapsing core of a massive star shrinks from thousands of kilometers across to just a few tens. Neutrinos, nearly massless particles, pour out in a torrent, carrying away most of the gravitational binding energy, nearly 10 to the 53rd ergs, a 1 with 53 zeros. This flood cools the proto-neutron star and helps drive a shock wave through the star's outer layers. If the shock is strong enough, the explosion succeeds, blasting the outer material into space and leaving behind a compact core. If not, falling material can crush the core further, collapsing it into a black hole and ending the Magnetars story before it begins. For the ones that survive, the first few minutes are critical. Inside, convection churns the hot, lepton-rich matter. Differential rotation winds magnetic field lines tighter and tighter. If the dynamo process works efficiently, the magnetic fields grow exponentially, shooting up to 10 to the 14th or even 10 to the 15th Gauss in just seconds. At that point, magnetic pressure becomes as strong as the internal gas and radiation pressure, shaping powerful winds, outflows, and even the structure of the supernova remnant around the newborn magnetar. With the help of the R process, these early winds may also make heavy elements. Material that is high in neutrons is sent into space, and elements like gold, platinum, and uranium are made by quickly capturing neutrons on seed nuclei. It's still not clear if magnetars make a big difference in the cosmic R process abundances, but their extreme conditions, high entropy, fast expansion, and strong neutrino fluxes make them interesting possibilities, along with neutron star mergers. Magnetic fields, so strong they shred atoms. Most of the time, when we think of magnetism on Earth, we think of fridge magnets, MRI machines, or the magnetic field that points compasses north. There is about a half Gauss of field around Earth, but the strongest laboratory magnets can only handle a few tens of thousands of Gauss before they break. Most neutron stars have magnetic fields that are 10 to the 12th Gauss, which is 1 trillion times stronger than Earth's. But magnetars push it to its limits, with fields as strong as 10 to the 15th Gauss. Magnetism changes the rules of atomic physics at that level. It doesn't just change the shape of matter. At these strengths, familiar intuition breaks down. An atom under normal conditions balances two forces. The positively charged nucleus attracts negatively charged electrons, while quantum mechanics spreads electrons into orbitals described by wave functions. This balance gives atoms their size, shape, and chemistry, but immerse that same atom in a magnetar strength field, and everything changes. The magnetic pressure dwarfs the electrostatic pull, holding electrons in place. Electron orbits collapse inward along the field direction, while stretching into thin, elongated cylinders, aligned with magnetic lines. Instead of roughly spherical electron clouds, atoms become needle-like structures, sometimes 100 times longer than wide, as if squashed and frozen into unnatural shapes by the field's grip. Calculations show that once magnetic fields climb above about 10 to the 9th Gauss, atoms themselves begin to deform. By the time you reach 10 to the 12th Gauss, even hydrogen, the simplest atom, stretches into a strange, tightly bound filament. At magnetar strengths near 10 to the 15th Gauss, the binding energy of electrons skyrockets. Instead of just tens of electron volts, it takes thousands to ionize atoms. This completely changes surface chemistry, conductivity, and how radiation escapes. Whole layers of a magnetar's crust may be made of exotic, magnetically confined matter unlike anything seen in normal stars or planets. And the effects don't stop at atoms. Ultra-strong magnetic fields also warp empty space itself through quantum electrodynamics, or QED. Normally, the vacuum is linear. Light waves pass through each other without interacting. But near the Schwinger limit, about 4.4 times 10 to the 13th Gauss, QED predicts the vacuum becomes nonlinear and polarized. Virtual electron-positron pairs constantly flicker in and out of existence, and the magnetic field lines them up, making empty space act like a birefringent crystal that splits light into different polarizations. Magnetars go beyond this critical field by factors of 10 or more. turning the regions around them into natural laboratories for physics first imagined in the 1930s, but only now being tested through observation. These same fields can pull particle-antiparticle pairs out of the vacuum entirely. When magnetic energy densities surpass nuclear binding energies, they spawn cascades of electrons, positrons, and gamma rays. This process helps fill magnetar magnetospheres with dense pair plasmas, feeding flares, radio bursts, and high-energy emissions we detect across galaxies. In effect, the magnetic field itself becomes an engine creating matter and light out of nothing but energy. Near the surface, magnetic pressure competes with and even exceeds gravitational and nuclear forces. The crust, already the densest solid known, feels enormous magnetic stresses twisting it over centuries until it fractures in sudden starquakes. These quakes rearrange magnetic fields violently, releasing stored energy as giant flares visible across the Milky Way and beyond. The famous 2004 flare from Magnetar SGR 1806-20 briefly outshone every other gamma-ray source in the sky, despite lying 50,000 light-years away. Had it occurred within 10 light-years, Earth's upper atmosphere might have been stripped of ozone, with catastrophic biological consequences. In normal physics, the fine structure constant alpha determines the strength of electromagnetic interactions. Atomic energy levels, chemical bonds, and photon scattering all depend on it. Under magnetar fields, effective coupling constants change as QED corrections grow huge, altering how particles scatter, how radiation propagates, and how matter behaves under compression. Plasma near the surface no longer follows textbook electrodynamics, but enters regimes where theory itself remains incomplete. Neutron stars may make things go even further. Matter turns into neutron-rich fluids, or maybe quark matter when its density goes above that of atomic nuclei. This is because neutrons break down into up, down, and strange quarks. Strong magnetic fields divide particle motion into Landau levels, which are separate energy bands that run perpendicular to the field. These levels change the equations of state that control pressure, density, and makeup. Some researchers say that very strong fields might even cause anisotropies inside the star, which would make it less spherical and could cause it to send out gravity waves as it spins. The crust that holds back a starquake. The bright X-rays and huge magnetic fields of a magnetar hide something that looks very normal: a solid crust. It is only 1 kilometer thick on top of a star that is 20 kilometers wide, so it looks weak compared to the powerful forces that are fighting below. Still, this crust is very important to the life of every magnetar. It's the shield that's keeping neutrons, superfluids, and magnetic fields that are tighter than anything else in the world from moving inside. It has pressures that build up slowly over years or hundreds of years until one day, with almost no notice, it breaks. A starquake is caused by that snap. It is so strong that it can shake the whole star, change its magnetic field, and send energy into space with the force of billions of nuclear bombs. To understand why this happens, we need to look at what the crust really is. After the supernova collapses a star into a neutron star or magnetar, the outer layers cool rapidly, solidifying into a lattice of atomic nuclei embedded in a sea of relativistic electrons. The densities climb steeply with depth. Near the surface, matter might be 10,000 times denser than lead, but only meters below it exceeds nuclear densities, where protons and neutrons themselves start dissolving into exotic forms. At the top lies the outer crust, made mostly of iron-like nuclei crushed so tightly that electrons become highly degenerate, zipping around near light speed. Deeper in, rising densities force electrons to merge with protons in nuclei via inverse beta decay, turning them into neutrons. This creates the inner crust, a bizarre region where neutron-rich nuclei coexist with a sea of free neutrons dripping out of nuclei like water from melting ice. Eventually, at the base, nuclear matter gives way to uniform neutron-rich fluid in the core, possibly mixed with superconducting protons, superfluid neutrons, and even stranger phases like quark matter. But for the crust, the most important ingredient is the magnetic field. Magnetars boast fields so intense they penetrate the entire star, threading through crust and core alike. As the interior cools and the field slowly evolves, it twists, shifts, and rearranges, driven by processes like Hall drift and ambipolar diffusion. These motions drag magnetic footpoints anchored in the solid crust, slowly winding up magnetic stresses over centuries. Think about making a ruler bend more and more every day. At first, it's easy to resist. If you bend it even more, tiny cracks start to appear and spread. When you push it to its limits, it finally breaks, letting out all the energy it has been holding in a split second. Magnetar crusts act in a way that is similar, but on a size that is hard to understand. The entire neutron star rings like a struck bell during these events. Quasi-periodic oscillations detected in the tails of giant flares hint at global seismic modes excited by crustal fractures. Some frequencies match theoretical models of torsional shear waves, rippling through the solid layers, offering a rare probe of conditions otherwise hidden beneath kilometers of degenerate matter. It's as though starquakes let us perform seismology on objects thousands of light years away. The crust does more than just devastation. What it does is also manage the changes in heat, magnetic fields, and rotational momentum between the core and the surface. Neutrons that are superfluid and below the crust move through quantized swirls, while the crust itself spins firmly. Glitches, which are sudden spin-ups seen in many neutron stars, are caused by sudden changes in rotational momentum between them. In magnetars, these glitches often happen at the same time as bursts, which suggests that they are caused by the same thing. A crustquake breaks magnetic fields and moves rotating energy around, shaking the whole star at the same time. Magnetar crust physics also connects to gravitational waves. Asymmetric fractures or magnetic deformations could create time-varying quadrupole moments, radiating gravitational waves detectable by future observatories, like the Einstein telescope or Cosmic Explorer. Though signals from individual quakes remain faint, newborn magnetars spinning rapidly after birth might emit stronger, longer-lasting waves if magnetic mountains or ellipticities persist before the star slows down. Magnetar starquakes, cracking a star like glass. When a magnetar finally gives up its centuries-long fight to stay together, it lets go in a flash of unimaginable fury. Starquakes happen when the magnetic stresses that run through the whole star are too much for even the hardest things that nature can make to handle. The crust breaks. Magnet field lines break and then join back together. A huge amount of energy is released in the form of radiation, particles, and seismic waves that make the star ring like a bell hit by a cosmic hammer. The magnetosphere changes shape almost quickly. The scale of this destruction is almost beyond imagination. A solar flare from our own sun, the biggest explosions in the solar system, releases about 10 to the 32nd ergs of energy. That already dwarfs anything humanity could ever produce. But a giant flare from a magnetar unleashes between 10 to the 44th and 10 to the 46th ergs in less than a single second. That's a billion trillion times more powerful than a large hydrogen bomb, and it equals the total energy our sun gives off in 100,000 years, all released in a single blinding burst. The process starts up quietly. The magnetar's magnetic field turns and moves over decades or centuries through processes such as Hall drift and ambipolar diffusion, leaving a mark on the solid rock. At first, the crust stays in place, bending like steel when it's under stress. But the magnetic pressure keeps going up, which bends the crust more and more until it breaks. At some key point, which is still not well understood, the top breaks apart in a terrible way. Everything moves quickly when it does. It's like cracks are moving at 1,000,000 kilometers per second across the surface. Lines of magnetic field that are rooted in the crust suddenly break and join, like solar flares on the sun but 1,000,000,000,000 times bigger. These reconnections speed up particles almost to the speed of light, sending a lot of gamma rays, X-rays, and electron-positron pairs into the magnetosphere. For people far away, the flare looks like a bright flash, and then a tail of pulsing X-rays that fades away as the magnetar spins. The most famous case occurred on December 27, 2004, when a giant flare erupted from Magnetar SGR 1806-20, located about 50,000 light-years away in the constellation Sagittarius. In just 0.2 seconds, it released more energy than the Sun emits in 100,000 years. Satellites near Earth were blinded. Detectors saturated as the initial spike swept past our planet. Even after scattering off the Moon, the radiation was so intense it noticeably affected Earth's ionosphere, a sobering reminder of what a closer event might do. Had SGR 1806-20 been within 10 light-years, the consequences for Earth's atmosphere, and possibly life, could have been catastrophic. Giant flares like this show a characteristic structure. First comes the initial spike, a fraction of a second long, releasing most of the energy as gamma rays and hard X-rays. Next follows a decaying tail lasting hundreds of seconds, modulated by the Magnetar's rotation period as hotspots on its surface swing in and out of view. Embedded in this tail, astronomers have detected quasi-periodic oscillations, QPOs, ripples in X-ray brightness at specific frequencies. These QPOs likely come from seismic vibrations ringing through the star after the crust shatters, offering a unique form of astroseismology for neutron stars. Different modes may shake different layers, torsional oscillations in the crust, Alfvén waves in the core, or coupled magnetoelastic modes involving both. By matching observed frequencies to theoretical models, physicists hope to probe the interior, densities, magnetic field configurations, even the possible presence of exotic matter phases like quark matter or hyperons at extreme depths. Starquakes also help explain why magnetars, unlike ordinary pulsars, emit so much high-energy radiation. Their persistent X-rays likely come from steady magnetic field decay heating the crust, while bursts and flares trace sudden magnetic reconfigurations during quakes. Some short gamma-ray bursts once attributed to distant cosmic cataclysms now appear linked to magnetars in nearby galaxies, their rapid timescales matching crustal fracture events rather than black hole formation. The physics resembles but vastly outscales solar flares. On the Sun, magnetic loops in the corona occasionally reconnect, accelerating particles and emitting X-rays. But solar magnetic fields measure only a few thousand Gauss, while magnetofields reach 10-15 Gauss. Energy scales with field strength squared, so even tiny changes in a magnetar's field release energies dwarfing anything in stellar astronomy besides supernovae or gamma-ray bursts. These flares may even contribute to mysterious fast radio bursts, FRBs, millisecond radio flashes detected across the universe. In 2020, one FRB called FRB 200428 coincided with an X-ray burst from the galactic magnetar SGR 1935 plus 2154, directly linking at least some FRBs to magnetar activity. Whether all FRBs come from magnetars remains unknown, but giant flares clearly produce conditions capable of generating coherent radio emission detectable across millions of light years. Rotation is also changed by starquakes. Glitches are unexpected spin-ups that are seen in some magnetars. They are thought to happen when cracks in the crust move rotational momentum from the superfluid inside to the rigid crust. Others show anti-glitches, which are rare spin-down events that might be connected to changes in the magnetosphere that happen during big flares. These changes in timing reveal more information about the physics inside the Earth that connects the rock, core, and changing magnetic fields. Magnetar flares that outshine entire galaxies. People in the universe pay attention when a magnetar breaks, when centuries of magnetic strain tear through its surface and the magnetosphere snaps like a trillion-mile-long rubber band. These are the giant flares, which are explosions that are so bright that for a short time they can shine brighter than billions of stars put together. A neutron star the size of Manhattan can shine brighter than galaxies that are spread out over millions of light years. The first time astronomers realized what they were dealing with came in March 1979. Detectors on multiple spacecraft, including Venera 11 and 12 and NASA's Helios 2, suddenly lit up with an intense gamma-ray flash. It wasn't coming from the Sun or a nuclear test on Earth. Its origin lay deep in space, in the Large Magellanic Cloud, 165,000 light-years away. That event, now known as the March 5th flare, released more energy in a fraction of a second than the Sun emits in 1,000 years. At the time, astronomers didn't yet have the word magnetar. They just knew something out there was frighteningly powerful. Decades later, the December 27, 2004 event from SGR 1806-20 drove the point home. Located about 50,000 light-years away, this magnetar released, in 0.2 of a second, as much energy as the Sun radiates over 100,000 years. Even after traveling across half the Milky Way, the flare saturated detectors, blinded instruments, and ionized Earth's upper atmosphere. Had it been only a few thousand light-years away, well outside what we'd normally call nearby, the radiation could have disrupted ozone chemistry or worse. If one went off within 10 light-years, the consequences for Earth's biosphere would be catastrophic, possibly rivaling mass extinction events. Each giant flare follows a recognizable pattern. First comes the initial spike, a blinding flash lasting milliseconds to a fraction of a second. This spike carries the lion's share of the energy, mostly in gamma rays and hard X-rays. Then comes the decaying tail, a pulsating afterglow lasting hundreds of seconds, modulated by the magnetar's spin as hotspots on the surface rotate into and out of view. Embedded within this tail, astronomers sometimes detect quasi-periodic oscillations, QPOs, tiny flickers in brightness repeating tens or hundreds of times per second. These QPOs likely come from the entire star vibrating after the crust fractures, letting scientists probe its interior structure through a kind of cosmic seismology. The energies at play push the limits of imagination. A solar flare tops out at about 10 to the 32nd ergs. A supernova, one of the brightest events in the universe, gives off around 10 to the 51st ergs, spread over weeks as it rises and fades. But a giant magnetar flare packs between 10 to the 44th and 10 to the 46th ergs into less than a single second. In that instant, it can outshine 1 million Milky Way galaxies. The only events that can rival or surpass them are gamma-ray bursts, explosions tied to collapsing massive stars, or merging neutron stars billions of light-years away. Magnetar flares, by contrast, erupt right here in our own galactic neighborhood. What powers such fury? The leading model points to magnetic reconnection, the same process behind solar flares, but scaled up by a factor of 1 trillion. As the magnetar's crust fractures, magnetic field lines anchored to it snap and reconnect in the magnetosphere, unleashing stored magnetic energy explosively. Particles accelerate to near light speed. Electron-positron pairs flood the magnetosphere. Gamma rays pour out in tightly beamed fireballs, expanding at relativistic speeds. Some energy channels into alpha waves racing along field lines back into the crust, heating it further and driving afterglows for days or weeks. We've now recorded 3 confirmed giant flares in our galaxy or its satellites. The 1979 March 5th event, the 1998 flare from SGR 1900+14, and the 2004 flare from SGR 1806-20. Several more candidates appear in other galaxies, identified by their short durations and extreme luminosities in gamma-ray observatories like Fermi and Swift. Some short gamma-ray bursts, SGRBs, once thought to come from neutron star mergers, may actually be extragalactic magnetar flares masquerading as distant cataclysms. Astronomers now wonder whether magnetar giant flares played roles in Earth's past. Some hypothesize that a nearby event hundreds of millions of years ago could explain spikes of certain isotopes like carbon-14 or beryllium-10 in tree rings and ice cores, though supernovae remain likelier culprits. Still, the possibility underscores the destructive potential these objects carry if one were close enough. Today's telescopes are always looking for them. Radio bands like CHIME and FAST listen for FRBs that might be tied to flares. Fermi, Swift, Integral and NICER keep an eye on the X-ray and gamma-ray skies. Future projects that use X-ray polarimetry, gravitational wave detectors, and even neutrino telescopes might be able to see the whole picture. Magnetic reconnection, crustal vibrations, particle acceleration, and radiation release all happening at the same time. Magnetic monstrosities, comparing magnetars to ordinary neutron stars. To fully understand how unique magnetars are, it helps to compare them to neutron stars and pulsars, which are more common. At first glance, all neutron stars seem to have the same birth story. A huge star burns through its nuclear fuel, its core falls apart under its own weight, and a 20-kilometer-wide piece of matter with more mass than the Sun forms. Neutron stars all spin quickly when they are born, give off X-rays as they cool, and have strong magnetic fields that they got from the stars that made them. But magnetars are on the very edge of this family picture. They break records so often that comparing them to regular neutron stars is like comparing storms to light winds. This magnetic excess drives many of the differences we see observationally. Ordinary pulsars radiate primarily through rotational energy loss. As they spin down over millions of years, they power radio beams, X-ray pulses, and sometimes high-energy gamma rays. Their magnetic fields act as conduits, extracting rotational energy and channeling it into particle winds and radiation. Magnetars, by contrast, glow mainly from magnetic energy decay rather than rotation. Their persistent X-ray luminosities far exceed what their spin-down rates can supply. In other words, while pulsars behave like spinning flywheels gradually slowing, magnetars behave like magnetic batteries discharging through bursts, flares, and steady X-ray heating as their fields rearrange and decay. Another distinction is shown by spin times. A lot of young pulsars spin 100 or more times every second. For example, the Crab pulsar spins 30 times every second, even though it is almost 1,000 years old. Magnetars, on the other hand, spin very slowly, usually only once every 2 to 12 seconds. At first, this doesn't make sense until you understand that their very strong magnetic fields stop their spinning much more effectively. It only takes a few thousand years for magnetars to slow down to a crawl compared to their younger or millisecond pulsar relatives because of magnetic dipole radiation, particle winds, and magnetospheric torques. Aging also diverges dramatically. Ordinary pulsars can remain active for tens of millions of years before fading into radio silence as dead neutron stars. Magnetars, with their ferocious magnetic decay, live fast and fade young. Most known magnetars appear only tens of thousands of years old. Beyond that, their fields likely decay below the threshold, driving giant flares and intense X-ray emission, leaving behind quieter neutron stars or perhaps objects like X-ray dim isolated neutron stars, XDINs, sometimes called the Magnificent Seven, whose thermal X-ray glow may represent aging, cooling magnetars in disguise. Emission behaviors reinforce the contrast. Pulsars give us regularity, metronomic radio pulses, predictable spin down, and steady light curves punctuated only rarely by glitches or mode changes. Magnetars thrive on unpredictability. They produce short bursts, giant flares, long-lived X-ray outbursts, glitches, anti-glitches, and sometimes transient radio pulses switching on and off after decades of silence. Their magnetic fields twist magnetospheres into unstable configurations, where small crustal shifts can trigger avalanches of reconnection events, releasing energies pulsars never approach. In ordinary neutron stars, the crust and atmosphere follow relatively familiar rules: ions in strong but not overwhelming fields, electron gases, thermal conduction shaping surface temperatures. Magnetar surfaces, by contrast, host fields so intense they quantize electron motion into Landau levels, alter photon opacities, and suppress thermal conductivity across field lines. Heat flows anisotropically, producing hot spots at magnetic poles, while the atmosphere itself may form condensed metallic states rather than gaseous layers, changing how X-rays escape into space. The innards of magnetars may also diverge. Ultra-strong fields running through the core could bend the star into forms that aren't spherical, which could send out gravity waves if the imbalances stay. Inside normal neutron stars, superconducting protons and superfluid neutrons already create strange magnetic and rotational dynamics. magnetar strength fields could push these phases into uncharted territory, changing glitch behavior, magnetic evolution, and seismic vibrations during giant flares. The death spin, how rotation and magnetism war over time. When a neutron star is first formed, it spins very quickly. Some babies spin hundreds of times every second because their dense centers hold on to the angular momentum from a parent star that was thousands of kilometers across and dying. At first, this spin uses up most of the star's energy. The new neutron star acts like a cosmic generator. Its fast spin and magnetic field work together to create winds, power radiation, and shape the clouds around it. As time goes on, however, rotation and magnetism start a long, uneven war. This war slowly drains the star's spin energy and, for magnetars in particular, sets the stage for catastrophic flares as their magnetic fields tighten their grip on every part of the star's life. At the center of this battle is a process called magnetic braking. A spinning, magnetized neutron star acts like a giant dipole antenna, radiating energy into space. Its magnetic field lines, anchored deep in the crust, sweep through the plasma around it, twisting and flinging particles outward in powerful winds. These winds carry away angular momentum, steadily slowing the star's rotation. The stronger the magnetic field, the faster this slowdown happens. Ordinary pulsars, with fields of about 10 to the 12th Gauss, can spin for millions of years before noticeably slowing. But magnetars, with fields 1,000 times stronger, burn through their rotational energy quickly, grinding down to spin periods of several seconds in just tens of thousands of years. This is shown in the magnetic dipole spin-down formula, which says that the spinning energy loss grows with the square of the magnetic field and shrinks with the cube of the spin period. Early on, a magnetar that spins very quickly might send out a huge amount of power as it slows down. This could cause events like superluminous supernovae or gamma-ray bursts when rotating energy mixes with ejecta in the area. But this phase doesn't last long. In a few hundred to 1,000 years, the spin slows down to seconds per turn, the rotational energy fades, and magnetic energy takes over the star's activity. But spin-down isn't easy. When angular momentum moves from the crust to the inner superfluid, magnetars experience sudden glitches, which are rapid spin-ups. Inside the neutron star, neutrons make a superfluid that doesn't stick to anything. It's held together by quantum swirls that make it spin. When magnetic braking slows down the crust, the superfluid moves behind and stores rotational momentum until vortices suddenly unpin and send it back to the crust. This causes a glitch in which the star spins faster for a short time before going back to its long-term slowdown. Magnetars also show rarer anti-glitches, sudden spin-downs possibly linked to magnetic reconfigurations in the crust or magnetosphere. During giant flares, for instance, rearranging magnetic fields could break the crust abruptly, transferring angular momentum outward rather than inward. These events reveal that spin evolution isn't a simple one-way decay, but a dynamic interaction between crust, core, and magnetosphere under extreme magnetic stresses. As rotation slows, the star's light cylinder, the distance where co-rotating magnetic field lines would move at light speed, expands outward. In ordinary pulsars, this gradually shuts down radio emission once the rotation period grows too long, producing the so-called pulsar death line, where pair production in the magnetosphere becomes insufficient to sustain radio beams. Magnetars cross this line quickly, yet remain active through magnetic energy decay rather than rotational power. Their X-ray and gamma-ray luminosities persist even when spin-down power falls orders of magnitude below what would be needed to explain observed emissions, proving magnetic fields, not rotation, dominate their energy output. Over thousands of years, both rotation and magnetism evolved together. Spin periods lengthen as magnetic braking continues, while magnetic fields themselves decay through processes like Hall drift, where currents in the crust rearrange magnetic field lines, and ohmic dissipation, where finite electrical conductivity slowly converts magnetic energy into heat. Ambipolar diffusion in the fluid core also transports magnetic flux outward over centuries to millennia. As fields decay, X-ray luminosities fade, giant flares grow rarer, and the star gradually transitions toward quiescence. Some theories suggest rotational energy at birth might even decide whether a neutron star becomes a magnetar at all. A rapidly spinning proto-neutron star could drive a dynamo mechanism, amplifying seed magnetic fields to magnetar strengths within seconds of formation. Slower rotators might fail to reach such fields, emerging as ordinary pulsars instead. If true, the initial spin sets the stage for the entire magnetic versus rotational history that follows. Twisted magnetospheres, the invisible monsters surrounding magnetars. There's more to a magnetar than meets the eye. Above the surface is the magnetosphere, which is a huge unseen ring of magnetic fields that controls everything in the star's path. Starquakes come from the crust, and the magnetic dynamo is in the core. The magnetosphere is where all of that energy flows out into the world. Particles move at speeds close to light, gamma-ray flares start, and plasma storms rage in conditions so intense that even our most powerful computer models have trouble capturing them. To picture a magnetar's magnetosphere, start with something familiar, Earth's magnetic field. It forms a roughly dipolar structure, with field lines emerging from one magnetic pole, arching outward, and re-entering at the opposite pole. Solar wind particles follow these lines, producing auroras when they crash into the atmosphere. Now take that picture and amplify it by a factor of 1 trillion. The magnetic field of a magnetar is so intense that it locks plasma into rigid structures, twisting space into complex geometries where the usual separation between matter and field blurs. Unlike ordinary pulsars, where the magnetosphere is mostly stable and dominated by open field lines carrying radio beams outward, magnetars host twisted magnetospheres packed with currents. When the star's crust shifts even slightly, through slow magnetic evolution or catastrophic quakes, it drags magnetic footpoints anchored in the crust, winding field lines above the surface like rubber bands stretched to their limits. The more they twist, the more magnetic energy they store, and the more unstable the entire system becomes. These twisted magnetospheres trap dense plasmas of electrons, positrons, and photons, creating conditions where magnetic reconnection can suddenly release stored energy explosively. That's why magnetars produce frequent short bursts of X-rays, and on rare occasions, giant flares rivaling the brightness of entire galaxies. The magnetosphere acts as both storage and trigger. Magnetic energy accumulates over years or centuries, then reconnects in milliseconds, accelerating particles and launching radiation across the electromagnetic spectrum. There are parts of the science here that we can't really test here on Earth. Magnetic reconnection is what turns saved magnetic energy into heat, particle motion, and high-speed acceleration in normal plasmas. This is the same process that causes solar flares, auroras on Earth, and even plasma bursts in fusion reactors like tokamaks. In magnetars, on the other hand, the magnetic fields are stronger than 10 to 14 Gauss, and they are so strong that they polarize the space itself. At those levels, strange quantum electrodynamic effects start to happen. Photons can split, and a single photon can turn into an electron-positron pair on its own. The plasma also acts in ways that are completely different from what we can do in the lab. Depending on the polarization, magnetic field lines spread and catch photons in different ways as they twist. Because of the strong field, light moving through empty space close to the magnetar splits into polarized modes that have slightly different refractive indices. This is called vacuum birefringence. X-ray polarimetry projects like IXPE are starting to find these effects, which is clear proof of QED processes that were predicted decades ago but can't be recreated in labs on Earth. Magnetospheric currents also heat the star's surface. Particles accelerated along field lines crash into the crust, creating hotspots emitting thermal X-rays. As the star rotates, these hotspots sweep across our line of sight, producing pulsating X-ray signals observed by telescopes like NICER and XMM Newton. When the magnetosphere twists more strongly, it traps heat longer, leading to outbursts where X-ray luminosity rises dramatically for months or years, before fading as the magnetosphere relaxes. The scale of these structures dwarfs the star itself. The neutron star measures only 20 kilometers across, but its closed magnetic field lines can extend thousands of kilometers outward before reaching the light cylinder, the radius where co-rotating field lines would exceed the speed of light. Inside this region, plasma remains tightly bound to the star's magnetic grip. Outside, field lines open into interstellar space, carrying winds of particles and electromagnetic radiation outward. Magnetars sometimes transition between quiescent and active states, depending on how twisted their magnetospheres become. In quiescence, the field relaxes, currents weaken, and X-ray luminosities stay relatively steady. During active phases, new twists inject energy, crustal fractures trigger reconnection, and bursts or giant flares erupt. Some magnetars even emit transient radio pulses after X-ray outbursts, suggesting magnetospheric reconfigurations temporarily create conditions similar to ordinary radio pulses before decaying again. Computer simulations show that as twists build, the magnetosphere approaches a critical point where even small disturbances trigger runaway reconnection events. This resembles how solar flares or substorms in Earth's magnetosphere behave, but under physics dominated by relativistic, quantum, and ultra-strong field effects. In these simulations, pair plasmas, alpha waves, and radiation all interact non-linearly, making magnetar magnetospheres some of the most challenging environments to model in astrophysics. This complexity is backed up by observations. Short X-ray bursts often happen close together in time, which suggests that magnetospheric avalanches happen when one reconnection event makes nearby areas less stable, similar to how earthquakes can cause aftershocks. Massive flares give off so much energy that they probably change the structure of the whole field, not just a few spots. When flare tails show quasi-periodic oscillations, QPOs, it could be because the crust and magnetosphere are vibrating together after such huge changes. Vacuum birefringence, when empty space becomes a prism. In our daily world, light moves through empty space without resistance. It doesn't bend, slow down, or split unless it passes through matter like glass, water, or a prism. But near a magnetar, the very idea of empty space breaks apart. Magnetic fields stronger than 10 to the 14th Gauss polarize the vacuum itself, turning what we think of as nothingness into a strange medium shaped by quantum effects. In this magnetized vacuum, light behaves as if space were a crystal, splitting into polarized beams that travel at slightly different speeds. This strange effect is known as vacuum birefringence, and magnetars are the only natural laboratories in the universe where it becomes a dominant reality. The roots of this effect go back to the 1930s when physicists studying quantum electrodynamics, QED, realized that in intense electromagnetic fields, the vacuum isn't truly empty. Instead, it teems with virtual particles, pairs of electrons and positrons flickering into existence for brief moments before annihilating. Under ordinary conditions, these quantum fluctuations remain invisible, averaging out so perfectly that light crosses empty space unaffected. But once the magnetic field climbs past about 4.4 times 10 to the 13th Gauss, the Schwinger limit, everything changes. Virtual electrons-positron pairs in the vacuum line up with the field, giving empty space an effective structure. Photons moving through this region interact differently depending on their polarization compared to the field direction. One polarization mode sees a slightly different refractive index than the other, so the two modes travel at different speeds. The result is that light splits into two polarized beams, just like it would when passing through a birefringent crystal such as calcite. On Earth, we can't come close to these conditions. The strongest pulsed magnets, or laser-driven fields, reach only about 10 to the 6th Gauss for a few millionths of a second, still billions of times weaker than what's needed. That's why magnetars are the only true natural laboratories for vacuum birefringence, with fields of 10 to the 14th to 10 to the 15th Gauss, turning quantum electrodynamics predictions into something we can actually observe. It's hard to find this result though. We use binoculars to catch X-rays or optical light after they've crossed the magnetized areas near the star, because we can't get close to a magnetar with equipment. If vacuum birefringence happens, the light that comes out of the vacuum should have a high level of linear polarization, which means that it should be lined with the shape of the magnetic field instead of having random angles. In 2016, astronomers reported tantalizing evidence using the Very Large Telescope, VLT, in Chile. Observing the isolated neutron star RxJ 1856.5-3754, they measured optical polarization around 16%, far higher than expected from interstellar dust alone. While not conclusive, this matched predictions for vacuum birefringence affecting light leaving the star's magnetized surface. More recently, NASA's Imaging X-ray Polarimetry Explorer, IXPE, launched in 2021, began mapping X-ray polarization from neutron stars, aiming to confirm QED effects under magnetic conditions unreachable in laboratories. When we think about photon splitting, which is another QED process that happens most often in very strong fields, the science gets more bizarre. Usually in a vacuum, one photon can't split into two lower energy photons because motion and energy don't change hands. In magnetar fields, however, the polarization of the vacuum breaks this rule, letting high-energy gamma-ray rays split into pairs of lower-energy photons. This might make the spectra of magnetar flares less sharp, which would stop the highest energy photons from leaving their magnetospheres. Similarly, one-photon pair production, a single photon transforming into an electron-positron pair without needing a collision partner, becomes possible because the magnetic field itself supplies the missing momentum balance. These processes fill magnetar magnetospheres with dense pair plasmas, shaping the radiation we detect after bursts and giant flares. What makes all this remarkable is that empty space, something we usually treat as the simplest, most featureless thing in physics, reveals hidden complexity when pushed to extremes. Around magnetars, the quantum vacuum behaves like a non-linear optical medium, splitting light, spawning particles, and altering radiation spectra in ways first imagined on chalkboards nearly a century ago. This isn't just for academics. Figuring out how light moves through magnetar fields can help us understand their X-ray pulse patterns, flare emissions, and maybe even where fast radio bursts, FRBs, come from. If photon splitting, or birefringence, controls how energy leaves magnetospheres, then it has a direct effect on what our telescopes see when these stars explode. Pair plasmas and exotic particles in magnetar fields. Near a magnetar, the vacuum doesn't stay empty for long. Magnetic fields stronger than 10 to the 14th Gauss don't just bend light or polarize space. They rip energy out of the field itself and convert it into matter. Electrons and positrons, created directly from pure energy through quantum electrodynamic processes, flood the magnetosphere in dense, high-speed seas called pair plasmas. These aren't just byproducts. They dominate the environment, shaping the radiation, the flares, and the entire electromagnetic character of a magnetar. The key mechanism starts with gamma-ray photons moving through these ultra-strong magnetic fields. Normally, a photon can't turn into a particle-antiparticle pair on its own because energy and momentum conservation prevent it. But in a magnetar's field, the magnetic field itself can absorb the extra momentum. That allows a single gamma-ray photon to transform into an electron and a positron. This process, called one-photon pair production, switches on efficiently once the magnetic field passes the quantum critical threshold of about 4.4 times 10 to the 13th Gauss, a limit magnetars exceed by at least an order of magnitude. As a result, the magnetosphere is filled with matter that was ripped out of the space. At relativistic speeds, electrons and positrons spin along magnetic field lines, giving off synchrotron radiation with X-ray and gamma-ray bands. These particles have opposite charges, but almost the same masses, so they react equally to electric and magnetic fields. This makes plasmas behave in ways that aren't seen in normal electron-ion plasmas found in stars, galaxies, or fusion tests on Earth. When magnetic reconnection events or starquakes send rapid bursts of energy through this environment, it becomes even stranger. When magnetic field lines bend and snap back together, they speed up particles to very high relativistic energies. This starts pair cascades, in which gamma rays create electron-positron pairs, which then create more gamma rays, which create even more pairs, and so on. In milliseconds, this chain reaction fills the magnetosphere with dense, hot plasma. Such cascades help explain why magnetar flares radiate so intensely across the electromagnetic spectrum. The initial magnetic energy release converts not only into photons but into matter-antimatter pairs, whose annihilation, scattering and radiation amplify the flare's brightness. During giant flares, pair densities may grow so high, the magnetosphere becomes optically thick to its own radiation, trapping photons until pressure forces them outward in explosive fireballs expanding at relativistic speeds. Theorists model these outflows as pair plasma fireballs, similar in spirit to those invoked in gamma-ray burst models, but confined by closed magnetic field lines rather than freely expanding into space. As the plasma cools and expands, radiation gradually escapes, producing the pulsating X-ray tails observed after giant flares. The star's rotation modulates this emission as hotspots swing in and out of view, while seismic vibrations imprint quasi-periodic oscillations hinting at crust and core physics deep below. Pair plasmas also influence how energy escapes magnetars in more subtle ways. In ordinary astrophysical plasmas, like the Sun's corona or Earth's magnetosphere, particle distributions and electric currents determine how magnetic energy converts into heat, light, and particle acceleration. In magnetars, pair plasmas interact with ultra-strong fields through processes like resonant Compton scattering, where X-ray photons repeatedly scatter off relativistic electrons and positrons, gaining or losing energy depending on magnetic geometry and plasma motion. This helps shape the hard X-ray tails observed in many magnetar spectra above 10 keV, where thermal emission from the surface mixes with non-thermal radiation from magnetospheric particles. Strange particles that don't fit into the standard model might even show up here. ALPs are hypothetical, light bosons that are thought to couple loosely to photons in strong magnetic fields, according to some ideas. If ALPs exist, they might change into photons and back again inside magnetar magnetospheres. This could change the polarization or make spectral patterns that future telescopes could see. Because of this, magnetars are natural labs for both astronomy and basic physics that can't be found on Earth. The dynamics of these plasmas remain challenging to simulate. Magnetic reconnection in ordinary environments already involves complex, turbulent physics. Adding relativistic speeds, quantum effects, and ultra-strong fields pushes models to their limits. Some simulations suggest twisted magnetospheres store energy for years before releasing it through avalanches of reconnection events, each triggering pair cascades that briefly turn the magnetosphere into an opaque, radiation-dominated fireball before relaxing again. From what we can see, hints come from a variety of bands. Missions that use X-rays to time things, like NICER and XMM Newton, follow flare light curves that are shaped by pair plasma opacity and cooling. Fermi and Integral have gamma-ray monitors that pick up the strongest bursts where pair cascades are getting out of hand. Radio telescopes that study fast radio bursts, FRBs, look for coherent emission that might be connected to pair plasma shocks in magnetar outflows. This is especially true now that FRB 200428 has been linked to a galactic magnetar flare in 2020. Magnetars as cosmic particle accelerators. When cosmic rays, those strange high-energy particles that hit Earth from space, reach energies higher than our most powerful machines can handle, scientists wonder what cosmic engines are speeding them up so quickly. Gamma-ray bursts, active galactic centers, and supernova shocks all play a part. Magnetars, on the other hand, stand out as unique options. They have rotating energies that are 1,000 trillion times stronger than Earth's and magnetic fields that are 1,000 trillion times stronger than Earth's. This means that particles can be sped up to incredible speeds, which may even explain some of the strongest cosmic rays ever found. The physics starts with magnetic reconnection and the loss of rotational energy. As a magnetar spins, its immense magnetic fields sweep through space, pulling plasma outward with them. The rotating magnetic dipole works like a unipolar inductor, generating electric fields of staggering strength along its open field lines. Any particles entering these zones are hurled across potential drops of 10 to the 15th up to 10 to the 17th volts, levels far beyond anything humanity can achieve. For comparison, the Large Hadron Collider, our most powerful accelerator, reaches about 10 to the 13th electron volts for protons. A magnetar, in theory, could push particles millions of times higher. Things get even worse when there are giant flares or when the top of a magnetar cracks. When magnets rejoin, a huge amount of stored magnetic energy is quickly released. This creates shocks and alpha waves that move through the magnetosphere. Particles traveling on these waves are moving very quickly, like electrons in the auroras on Earth, but on a much larger scale. Some models say that magnetars might be able to push protons and even heavy nuclei to levels of cosmic rays with more than 10 to the 20th electron volts of energy. That's so far out there that it goes against what we know about physics and even what our devices can measure. Evidence linking magnetars to cosmic rays remains circumstantial but intriguing. The arrival directions of the highest energy cosmic rays detected by observatories like Pierre-Auger and Telescope Array show hints of correlation with star-forming galaxies where magnetars might be common. Young, rapidly spinning magnetars born in superluminous supernovae or gamma-ray bursts could inject cosmic rays into surrounding space during their brief, violent early lives. Magnetars may also power pulsar wind nebulae, PWN, expanding bubbles of relativistic particles and magnetic fields trapped inside supernova remnants. Ordinary pulsars like the Crab accelerate electrons and positrons, producing bright synchrotron radiation across radio to gamma-ray wavelengths. A magnetar wind nebula, supercharged by magnetic energy and pair cascades, could drive even more extreme particle acceleration, though observational evidence for such nebulae remains sparse compared to ordinary pulsars. The acceleration mechanisms likely involve several processes operating together. Unipolar induction arises from the rotating magnetic dipole, driving electric potentials along open field lines near the magnetic poles. Magnetic reconnection in twisted magnetospheres converts magnetic energy into particle kinetic energy explosively during flares. Shock acceleration occurs when outflows from giant flares slam into surrounding media, creating relativistic shocks where particles gain energy through repeated crossings, a process known as Fermi acceleration. Some particles get away into space between the stars, while others get stuck and send out synchrotron and curve radiation as they spin along field lines. Gamma rays with a lot of energy are made when charges follow curved magnetic field lines close to the star's surface. This is called curvature radiation. These gamma rays could start more pair cascades, which would feed back into the magnetospheric plasma environment and create bursts, flares, and long-lasting emissions. Gamma-ray telescopes like Fermi-Late mostly find magnetars through bursts and flares, not through steady high-energy output. But short-lived streams from giant flares could speed up particles that then combine with interstellar gas or radiation fields to create secondary gamma rays, neutrinos, or cosmic rays that reach Earth millions of years later. Magnetar flares have been suggested by some experts as the cause of the high-energy neutrinos found by IceCube. But there aren't any solid links between the two yet. If magnetars really can send cosmic rays to very high speeds, they make it hard to understand how those particles move through space. Cosmic rays start losing energy when they hit photons from the cosmic microwave background at energies above about 5 times 10 to the 19th electron volts. The GZK cutoff is the name for this event. That means that any particles we find with those energies must have come from not too far away, within 100 million light-years. In that range, magnetars in close galaxies that are making stars, or even in our own Milky Way, could be adding to the flow of very high-energy cosmic rays that we see. Gamma-ray repeaters, the magnetar connection. Astronomers were already having trouble with strange signs called soft gamma ray repeaters, SGRs, before anyone even knew the word magnetar. Unlike gamma ray bursts, GRBs, which only flashed once and then disappeared, SGRs happened over and over again from the same spot in the sky for months or even years. They didn't act like supernovae, pulsars, or any other known celestial body at the time. There may be a strange, overactive engine hiding in the Milky Way and its friends. This engine could store energy for decades and then release it over and over again. The breakthrough came with the March 5, 1979 event. Detectors aboard several spacecraft, including Venera 11 and 12, suddenly recorded an intense gamma-ray burst lasting less than a second, followed by a pulsating tail repeating every 8 seconds for several minutes. This came from the direction of the Large Magellanic Cloud, a satellite galaxy 165,000 light-years away. The periodic tail revealed a rotating object, while the multiple bursts from the same source over following years showed it wasn't a one-off cataclysm like a supernova. Something survived each explosion to flare again later. By the 1980s and 1990s, astronomers had pinned down several sources of these strange outbursts: SGR 0526, 66 in the Large Magellanic Cloud, SGR 1900 plus 14, SGR 18 06-20, and others. Each one produced repeating gamma-ray flashes with energies far beyond ordinary stellar flares. Most of the bursts were brief, less than a second long, but still powerful enough to release between 10 to the 39th and 10 to the 41st ergs. And every so often, they erupted in giant flares, unleashing 10 to the 44th to 10 to the 46th ergs in just milliseconds, flares so intense they rivaled the combined brightness of entire galaxies. The repeating nature ruled out catastrophic events like neutron star mergers or collapsing massive stars. Instead, models focused on neutron stars with unstable magnetic fields or accretion disks feeding sporadic explosions. But no known pulsars or X-ray binaries produced bursts this powerful. Something new had to be hiding behind these signals. The puzzle became more clear after the big flare from SGR 1900 plus 14 on August 27, 1998. Like the 1979 event, it had a bright spike of gamma rays followed by a pulsing tail that happened at the rate of the star's spin, which in this case was 5.16 seconds. As the star's surface cooled down after being heated, X-ray afterglows stayed for weeks. Radio afterglows showed shockwaves moving through space at speeds that are faster than light. It wasn't just a few explosions on the surface. The star and its atmosphere let out huge amounts of magnetic energy all at once. By the early 2000s, theorists had converged on the magnetar model. A neutron star with a magnetic field above 1014 Gauss stores enormous energy in twisted, evolving magnetic fields. As these fields shift inside the star, they stress the solid crust until it cracks in starquakes. The sudden motion of magnetic footpoints in the crust triggers magnetic reconnection in the magnetosphere, much like solar flares, but scaled up by a factor of 1 trillion. The energy release accelerates particles, floods the magnetosphere with electron-positron pairs, and emits gamma rays across open field lines towards space. This explains why SGRs repeat. The star survives each flare, gradually rebuilding magnetic stresses until the next crustal failure. Small shifts produce ordinary bursts. Massive rearrangements trigger giant flares visible across galaxies. The spin periods of SGRs, seconds rather than milliseconds, match magnetars spinning down rapidly under magnetic braking, while their persistent X-ray luminosities exceed what rotational energy alone could supply, pointing to magnetic energy decay as the main power source. Observations over the last 2 decades confirmed these links. Many SGRs show X-ray outbursts lasting months after major flares, consistent with crustal heating and magnetospheric untwisting. Their spin-down rates imply dipole fields above 1014 Gauss, squarely in magnetar territory. Some even switch between quiet and active phases unpredictably, producing dozens of bursts in days before falling silent for years. The most stunning was on December 27, 2004, when SGR 1806-20 made the biggest giant flare ever seen. It was brighter than all the other gamma-ray sources in the sky put together for 0.2 seconds, overwhelming instruments even after reflecting off the moon. But the star lived, and in later years it continued to send out bursts. SGRs are basically different from classical gamma-ray bursts that are linked to one-time star deaths because they can explode over and over again without destroying themselves. Some short-duration GRBs detected in other galaxies may actually be extragalactic magnetar giant flares masquerading as distant cataclysms. Their brief durations, hard spectra, and occasional localizations to star-forming galaxies support this idea, though most short GRBs likely come from neutron star mergers instead. A new element is added by the link between SGRs and fast radio bursts, FRBs. In April 2020, the galactic magnetar SGR 1935 plus 2154 sent out both an X-ray burst and a bright millisecond radio flash at the same time. This showed that at least some FRBs come from magnetar flares. It is still not clear if FRBs that happen over and over in different parts of the universe are caused by the same events, but magnetars are now the most likely culprits. The fast radio burst mystery and magnetar flares. Astronomers were looking through old data from Australia's Parkes radio station in 2007 and came across something strange, a radio flash that was only a millisecond long, but had as much energy as the sun gives off in days. It came from very far away in the sky, but it was gone in 1,000th of a second. They called it the Lorimer burst, after Duncan Lorimer, who found it. Soon after, more of these flashes were seen in other telescope records. Astronomers thought they saw short, strong radio waves all over the universe that were different from anything they had seen before. These became known as fast radio bursts, FRBs, and they only got stranger. Most appeared once and never repeated. Others, like FRB 121102, produced dozens of bursts over months, even years. Some showed complex structures in their light curves, with multiple peaks or varying brightness. All arrived with dispersion measures far exceeding what our own galaxy's interstellar plasma could explain, proving they came from distant galaxies billions of light-years away. The mystery deepened as telescopes like CHIME in Canada, ASKP in Australia, and FAST in China detected hundreds of FRBs. Their energies rivaled the annual output of entire stars, yet they lasted less than a heartbeat. What could possibly produce such intense, coherent radio flashes on millisecond timescales? Dozens of models appeared, merging neutron stars, collapsing black holes, cosmic strings, even alien transmitters in the wilder corners of speculation. But one candidate grew steadily stronger: magnetars. Their giant flares already produced gamma rays and X-rays visible across galaxies. Could similar magnetic reconnection events also generate coherent radio bursts? Theory said yes. Magnetic reconnection in ultra-strong fields can accelerate particles to extreme energies, creating relativistic outflows slamming into surrounding plasma. At these shock fronts, conditions may favor coherent emission, where vast numbers of particles radiate in phase, amplifying the signal enormously, like a natural cosmic radio laser, or MARSA. Unlike ordinary synchrotron radiation, which is incoherent and spread out in frequency, coherent processes can produce the bright, narrow, millisecond pulses seen in FRBs. The smoking gun arrived in April 2020. The galactic magnetar SGR 1935 plus 2154, already known for X-ray bursts, suddenly produced a millisecond radio flash bright enough to rival FRBs if placed in another galaxy. Simultaneously, X-ray satellites detected a burst from the same source, proving the two signals came from one event. For the first time, astronomers had caught a magnetar in the act of producing an FRB-like signal. Everything changed. Even though not all FRBs have to come from magnetars, some could be caused by neutron star mergers or other strange engines. The event in 2020 proved that at least one way works: young, busy magnetars releasing magnetic energy. Details are still being argued over. Some models use magnetospheric reconnection to explain how crustal shifts can twist magnetic field lines until they break. This speeds up particles along closed field lines and directly sends out radio waves. Others, like shocks from the outside, where magnetic events send relativistic ejecta crashing into the plasma around them. This changes the kinetic energy into coordinated radio emission at the shock front. It's possible that both processes work in different situations, which is why some FRBs show more than once and then disappear forever. Sources like FRB 121102 burst hundreds of times, sometimes clustering over hours before falling silent for weeks. If these come from magnetars, they may represent young stars with frequent magnetic reconnection events, gradually calming as magnetic fields decay over centuries. Single, non-repeating FRBs might arise from catastrophic flares exhausting magnetic energy in one go, or from entirely different engines like neutron star mergers. Knowing more about polarization is like adding more pieces to a puzzle. A lot of FRBs have almost 100% linear polarization, which means they give off coherent radiation in very well-ordered magnetic fields. This is exactly what magnetar magnetospheres do. Some bursts also show Faraday's spin, which twists polarization angles as they move through magnetized plasma close to the source. This is also consistent with young magnetars being in dense magnetized places like supernova remnants. Even the staggering brightness starts to add up. A giant magnetar flare can release as much as 10 to the 46th ergs in just a few milliseconds. If only a tiny slice of that energy, even as little as 1/10 of 1%, is converted into coherent radio waves, it would be enough to explain the energies we see in fast radio bursts. With magnetic fields around 10 to the 15th Gauss, magnetars have more than enough stored energy to keep producing such outbursts repeatedly, potentially for hundreds of years, before their fields decay below the level needed to power giant flares. FRBs are now being found in host galaxies in real time by studies that are still going on. Some of them come from dwarf galaxies where stars are still being formed, which is exactly where there should be a lot of young magnetars after a supernova. Others form in more normal galaxies, which suggests that there are more than one way they came to be. When magnetars collide with surrounding matter, you can't live in a magnetar by yourself. As it forms, it is surrounded by spinning gas, expanding ejecta, and sometimes the thick stellar winds of the star that made it. Cracks, bursts, and explodes with big lights and bursts of power that shoot outward. They hit things nearby, which changes the shape of nebulae, sends shockwaves through space, and lights up some areas in both beautiful and violent ways. The process starts in the first seconds after the supernova, when the star's core collapses into a neutron star, or in rare cases, a magnetar. The outer layers blast outward at thousands of kilometers per second. The newborn magnetar sits at the center of this expanding shell, spinning rapidly and bristling with magnetic energy. Its rotation and magnetic fields launch winds of relativistic particles, carrying away rotational and magnetic energy into the surrounding debris. As this wind slams into the slower-moving supernova ejecta, it creates a termination shock where the relativistic outflow decelerates abruptly. Behind this shock, particles accelerate to extreme energies, producing synchrotron radiation across radio to X-ray wavelengths. Over time, the shocked wind inflates a bubble of magnetized plasma called a pulsar wind nebula, PWN, the same mechanism powering the famous Crab Nebula around an ordinary young pulsar. For magnetars, the energy injection can be even more intense, especially if rapid initial rotation dumps enormous spin-down power into the surrounding material within the first hours or days after birth. Superluminous supernovae, SLS-NA, may have magnetars that power their expanding ejecta, which makes them shine much brighter than nuclear decay alone could. It keeps the ejecta hot and bright for weeks or months by putting energy into it from the inside as the magnetar slows down. The resulting light curves fit what has been seen in a number of SLS-NE, which suggests that baby magnetars can sometimes recharge the remains of supernovae long after the initial explosion. But even after the supernova glow goes out, a magnetar's strong winds and wild flares continue to shape the space around it. It is possible for X-ray bursts and huge flares to send out streams of relativistic particles and electromagnetic waves. They create bow shocks and blast waves when they hit close gas, which speeds up particles and sets off afterglows in radio and X-ray light. One striking example was on December 27, 2004, when SGR 1806-20 sent out a huge flare that was so strong that it made a beautiful radio nebula. Astronomers watched it grow for weeks as the relativistic outflow cut through space, bringing about 10 to the 46th ergs of energy. Over centuries, repeated flares may carve out magnetized cavities in the interstellar medium, much like stellar winds from massive stars create bubbles tens of light years across. But whereas ordinary stellar winds flow steadily, magnetar outflows arrive in violent, intermittent blasts, each injecting energy impulsively rather than continuously. This could produce complex structures, shocked shells, relativistic particles, and turbulence mixing across scales from light seconds near the star to parsecs in the surrounding medium. Some magnetars move rapidly through space at hundreds of kilometers per second, kicked during the asymmetry of their birth supernovae. As they plow through interstellar gas, their relativistic winds form bow-shock nebula resembling the wakes of supersonic boats. The magnetic fields, particle acceleration, and synchrotron radiation in these bow shocks may reveal the magnetar's wind power, velocity, and interaction history with the interstellar medium. Magnetar streams may sometimes run into thick molecular clouds close to places where stars are being formed. Through hadronic interactions, relativistic particles can smash into this kind of material and make X-rays, gamma rays, or even neutrinos that are not heated. Neutrino signs from magnetars have not yet been proven, but future detectors like IceCube Gen 2 may check to see if magnetar flares add to the high-energy neutrino background. Some experts think that fast radio bursts, FRBs, connected to magnetars might involve collisions with matter in the area. In these models, a flare sends out a relativistic shell that hits a wind nebula or supernova ejector that is already there. The shock that follows speeds up particles and causes coherent maser emission, which is what we see as millisecond radio flashes. This might be why some FRBs happen more than once, the same magnetar sending out multiple flares that energize the space around it. Interactions with surrounding matter may also leave long-lived afterglows detectable across the electromagnetic spectrum. For instance, after the 2004 SGR 1806-20 flare, radio telescopes tracked an expanding nebula for months, measuring its energy, expansion speed, and polarization. These observations revealed a mildly relativistic outflow with magnetic fields shaping its evolution, direct evidence of how magnetar flares dump energy into their surroundings. The fate of planets around magnetars. Normal stars can support stable planetary systems for billions of years. Magnetars, on the other hand, are so unfriendly that any close planet would be destroyed by almost every physical force you can think of. Radiation, magnetic fields, particle winds, and even mechanical shocks from flares make magnetars the most dangerous landlords in the universe. Astronomers find magnetars very interesting, but the conditions that make them so dangerous for life, or even the atmosphere of a planet, are almost impossible for life to survive. Consider first the birth environment. When a massive star collapses into a neutron star or magnetar, the supernova explosion itself scours any nearby planets. Outer planets might survive gravitationally bound if they orbit far enough away, but anything within a few astronomical units risks either being vaporized by the radiation flash or engulfed by the expanding stellar envelope. Even if a planet avoids direct destruction, the explosion injects energy into surrounding space, stripping atmospheres and destabilizing orbits. Now picture a planet that somehow makes it through the chaos of the supernova or forms later from the leftover debris orbiting a magnetar. Survival is only temporary because the environment around a magnetar is hostile beyond imagination. Its magnetic field between 10 to the 14th and 10 to the 15th Gauss near the surface stretches far into space, constantly shifting and snapping during starquakes and giant flares. Any planet unlucky enough to cross those magnetic field lines would be hit with induced electric currents powerful enough to melt its crust, strip and ionize its atmosphere, and unleash radiation storms thousands of times stronger than the worst solar flares ever seen in our own system. Radiation itself poses an even deadlier threat. Ordinary stars emit visible light and moderate levels of X-rays and ultraviolet radiation. Planets with atmospheres or magnetic fields can shield life from most of it. Magnetars, by contrast, emit persistent X-ray and gamma-ray fluxes even in quiescence, powered by magnetic field decay rather than fusion. During giant flares, they release in milliseconds as much energy as the Sun radiates over 100,000 years. Most of it as high-energy photons capable of sterilizing planetary surfaces instantly. The 2004 giant flare from SGR 1806-20, located 50,000 light-years away, measurably disturbed Earth's ionosphere despite such enormous distance. Had it erupted within 10 light-years, models suggest it could have destroyed much of our ozone layer, exposing the biosphere to lethal ultraviolet radiation from the Sun. Any planet in a system with an active magnetar would endure such events repeatedly over thousands of years, preventing stable atmospheres or long-term habitability. Similar to pulsar winds but often more intense, these outflows carry relativistic electrons, positrons, and possibly heavy ions accelerated by the star's rotating magnetic field. When such winds slam into a planetary magnetosphere, or what remains of one, they deposit energy that can erode atmospheres over time, much like the solar wind gradually strips unprotected worlds like Mars. Around a magnetar, this process accelerates dramatically, potentially removing entire atmospheres in just thousands of years. Even the security of orbits is called into question. As magnetars lose their ability to spin and their magnetic fields weaken, they send out unbalanced winds and maybe even gravity waves if their insides keep deforming. These processes take away both energy and rotational momentum, which slightly changes the paths of circles nearby. If a planet makes it through the supernova, it might slowly spiral outward due to wind-driven mass loss, or it could spiral inward if gravity forces make the system unstable after the parent star dies. However, planets have been found orbiting regular pulsars. One well-known example is the system around PSR b 1257 plus 12, which has 3 planets of Earth mass orbiting a millisecond pulsar 2,300 light-years away. It's more likely that these planets formed from fallback disks after the supernova than from the original system of stars. Could the same thing happen near magnetars? In theory, yes. The stuff that was thrown out during the explosion could settle into a disk, where it would cool and stick together over millions of years to form planetesimals. But any such planets would face conditions far worse than those near ordinary pulsars. Magnetar flares exceed typical pulsar emissions by orders of magnitude, while their magnetic fields dominate space out to thousands of kilometers. A planet forming tens of astronomical units away might avoid tidal disruption, but would still endure repeated gamma-ray sterilization events over the magnetar's active lifetime. Even strange concepts like life below the surface or thick atmospheres that protect us from harm have a hard time here. Gamma rays with a lot of energy can go deep into the crusts of planets and heat and cleanse rock layers meters below the surface by sending out showers of particles. Flares frequently wear away or change the chemicals in the upper layers of the atmosphere, which stops long-term stability. When fields outside of Earth that are 1 trillion times stronger than Earth's dominate any planetary engine, magnetic shielding doesn't help much. Magnetic mountains and gravitational waves. We usually think of rocky peaks on Earth or huge volcanoes on other worlds when we think of mountains. With their strong magnetic fields and heavy gravity, magnetars can build mountains that are unlike anything else in the solar system. These mountains are so big that they send gravitational waves through space. These so-called magnetic mountains are only a few centimeters or meters above the very dense surface of a magnetar. However, they allow the star to shake space-time itself because they mess up the star's perfect circular symmetry. The story begins with magnetic pressure competing against gravity. On a neutron star, gravity dominates nearly everything. A mountain made of rock as we know it cannot exist because the star's gravity crushes matter into uniform layers only millimeters thick near the surface. Yet magnetic fields add another force to the equation. If strong enough, they push outward, distorting the crust and even the fluid interior beneath. When the magnetic field isn't perfectly symmetric, it creates pressure imbalances that deform the star into an ellipsoidal shape rather than a perfect sphere. These deformations, though tiny in height, carry staggering mass because the entire crust and outer core shift under magnetic stresses. As the magnetar spins, these asymmetries rotate with it. A perfectly spherical body rotating in space emits no gravitational waves because its mass distribution stays uniform, but a lumpy or distorted body radiates gravitational waves at twice its rotation frequency, carrying energy away as ripples in space-time. The stronger the distortion, the brighter the gravitational wave signal, at least in principle. The strongest signals would come from young, rapidly spinning magnetars. Right after birth, some magnetars may rotate hundreds of times per second, their magnetic fields twisting and stressing the crust before the star spins down over thousands of years. If ellipticities persist during this early, fast-spinning phase, the star could emit detectable gravitational waves carrying away both rotational and magnetic energy. Some researchers propose that gravitational wave losses, not just magnetic braking, might help slow young magnetars so quickly after birth. Detecting such signals, however, challenges even the most sensitive instruments. Continuous gravitational waves from a single rotating source produce extremely faint strains in space-time, tiny compared to the brief, powerful chirps from merging black holes or neutron stars already observed by LIGO and Virgo. Searches for continuous waves require long integration times, precise knowledge of the source's position and rotation frequency, and luck. The ellipticity must be large enough and the distance close enough for the signal to rise above detector noise. So far, no continuous gravitational waves from magnetars have been detected. Upper limits from LIGO observations constrain ellipticities for known neutron stars to below about 10^5 in many cases, leaving room for theoretical models but no direct proof yet. Future observatories like the Einstein Telescope and Cosmic Explorer will push sensitivities far enough to test whether newborn magnetars in nearby galaxies shed energy through gravitational waves during their first months or years. Magnetic mountains also tie into starquakes and seismic oscillations observed after giant flares. When the crust fractures, magnetic fields may rearrange globally, changing the star's ellipticity abruptly. If the deformation shifts quickly enough, it could launch not only electromagnetic radiation, but also a burst of gravitational waves accompanying the flare. Such signals would be short rather than continuous, potentially detectable if a giant flare erupted within our own galaxy while advanced gravitational wave detectors were online. Some models even connect magnetic mountains to fast radio bursts, FRBs. If magnetic stresses gradually build ellipticity until the crust yields catastrophically, the resulting magnetic reconnection might power both coherent radio bursts and gravitational wave bursts simultaneously. Coordinated searches across radio, X-ray, gamma-ray, and gravitational wave observatories could test these multi-messenger predictions in coming decades. The physics behind building these mountains involves exotic states of matter. Neutron star crusts consist of nuclei arranged in crystal lattices under densities millions of times greater than any terrestrial metal. Deeper layers approach the so-called nuclear pasta phases, lasagna-like sheets or spaghetti-like filaments of nuclear matter predicted at the crust core boundary. Magnetic fields threading these layers interact with superfluid neutrons and superconducting protons, creating stresses difficult to model, even with modern supercomputers. Whether magnetic pressure concentrates in localized mountain regions, or spreads smoothly through the crust depends on this poorly understood microphysics. Neutrino firestorms from magnetar birth. When a massive star collapses into a neutron star, or in rare cases, a magnetar, the most powerful outburst isn't in light gamma rays or even gravitational waves. It's in neutrinos, the ghost-like particles that barely interact with matter. In those first tens of seconds after collapse, nearly all of the released gravitational binding energy, about 10 to the 53rd ergs, pours out as an immense flood of neutrinos. To put that in scale, it's more energy than every star in the observable universe gives off in light over the same period. This neutrino storm begins deep inside the collapsing core. As the implosion tightens, densities soar past nuclear levels, over 10 to the 14th grams per cubic centimeter, while temperatures shoot above 10 to the 11th kelvins, hot enough to melt atomic nuclei into a seething mix of neutrons, protons, electrons, and neutrinos. When the inner core finally halts at nuclear density, it rebounds slightly, sending a shockwave out into the still falling outer layers. But that shock quickly stalls, losing its punch as it burns energy, breaking apart heavy nuclei into free nucleons. Neutrinos are the main part of this picture. In the next few hundred milliseconds, the proto-neutron star will send out neutrinos of all types, including electron, muon, tau, and their antiparticles. These neutrinos will carry energy and lepton number away from the star. It is said that the star gives off more neutrinos per cubic centimeter per second than the Sun does in its whole volume. However, neutrinos are much more easily able to escape than photons, which are stuck inside normal stars for millions of years. This is because neutrinos only interact with electromagnetic fields. For magnetars, this stage plays out much like it does for ordinary neutron stars, but with a dramatic difference. Rapid rotation and ultra-strong magnetic fields reshape the entire process. Dynamo action in the newborn star can amplify seed magnetic fields to around 10 to the 15th Gauss within just seconds, while differential rotation twists magnetic toroids deep inside the fluid core. Meanwhile, neutrino-driven convection churns the star as hot matter rises and cooler matter sinks, fueling both the growth of the magnetic field and the intense flood of neutrinos streaming outward. In the very first second after collapse, the proto-neutron star unleashes a neutrino burst carrying several times 10 to the 52nd ergs, momentarily outshining the entire visible universe in neutrino light alone. Over the next 10 seconds, cooling and deleptonization, the process where electron neutrinos convert protons into neutrons, drain away the rest of the gravitational binding energy. What remains is a neutron star, now with its temperature falling below 10 to the 10th kelvins, cooling into the next stage of its life. During this window, neutrino heating just outside the proto-neutron star may help revive the stalled shock wave, blowing off the star's outer layers in the supernova explosion. If the neutrino heating succeeds, the star explodes, leaving the neutron star or magnetar behind. If not, fallback material may swallow the proto-neutron star into a black hole instead. The neutrino-driven wind emerging in the first seconds also seeds the surrounding space with heavy elements through our process nuclear synthesis, possibly forging gold, platinum, and uranium under neutron-rich conditions before the wind thins out. The neutrino firestorm also sets the star's initial conditions for everything that follows: magnetic field configuration, spin period, temperature profile, and crust formation. As the proto-neutron star cools below nuclear dissociation temperatures, its outer layers solidify into the crust that later cracks during magnetar flares. The magnetic fields frozen into this crust evolve over thousands of years, storing energy for future starquakes and giant flares that make magnetars famous. Direct evidence for these neutrino firestorms came from SN 1987A, when detectors like Kamiokande 2 in Japan and IMB in the US caught 24 neutrinos over 13 seconds from a supernova 168,000 light-years away in the Large Magellanic Cloud. That tiny trickle confirmed models predicting that nearly all supernova energy escapes via neutrinos rather than light. A similar event in our own galaxy today would trigger detectors worldwide with thousands of neutrinos, letting us watch a neutron star or magnetar forming in real time through particles rather than photons. Neutrino telescopes like Hypercameo-Candy and Dune will make this picture a lot clearer in the future. If a nearby supernova creates a magnetar, scientists could follow its neutrino brightness curve second by second to see if fast spinning or very strong magnetic fields change how neutron stars cool, what neutrinos they produce, or how they explode compared to normal neutron stars. Cooling curves and thermal X-ray emission. A newborn magnetar starts out hotter than almost anything else in the cosmos. In the moments right after its birth, its core temperature soars above 10 to the 11th kelvins, hot enough to completely vaporize atomic nuclei into a uniform soup of neutrons, protons, electrons, and neutrinos. But this furnace doesn't last long. Within just seconds, the neutrino firestorm that erupts at collapse carries away most of the gravitational binding energy, cooling the star down to about 10 to the 10th kelvins. From there, over the course of hours to days, it continues to cool rapidly. Its crust begins to solidify, its interior superfluids start to freeze, and the foundations of its long-term thermal and magnetic evolution are set. Patterns that will define the magnetar's behavior for thousands of years. For ordinary neutron stars, cooling proceeds through well-studied stages. First comes the neutrino cooling era, lasting up to about 100,000 years, where most heat escapes as neutrinos from the dense core via processes like the modified and direct Urca reactions. Later, the photon cooling era takes over, with heat escaping from the surface as thermal X-rays rather than neutrinos. The surface temperature gradually falls from millions of kelvins to hundreds of thousands over hundreds of thousands to millions of years, eventually becoming too cold to detect in X-rays at all. Magnetars make this easy picture a lot more difficult to understand. Through ohmic dissipation and Hall drift, which happen when electric currents break down and reorder, their magnetic fields add more heat to the crust and upper layers. Magnetars don't just cool down, they go through a tug-of-war between losing heat through neutrinos and photons and gaining heat through the breakdown of magnetic fields, which turns magnetic energy into thermal energy. This answers one of the biggest mysteries in the world of astronomy. Magnetars look hotter than regular neutron stars of the same age. Magnetars that are tens of thousands of years old often have surface temperatures above 37 million kelvins, while normal pulsars of the same age have temperatures below 1-2 million kelvins. The extra heat comes from magnetic energy stored in the rock and outer core. This energy slowly fades away over millions of years, slowing the change from neutrino-dominated cooling to photon-dominated cooling. Theoretical cooling curves, plots of surface temperature versus time, reflect this competition. Models without magnetic field decay predict steep temperature drops after the first 1,000 years. Add magnetic heating and the curves flatten, producing higher temperatures over longer timescales. The stronger the initial field, especially above 1015 Gauss, the longer the star stays hot, sometimes for hundreds of thousands of years if decay proceeds slowly enough. Crustal physics is important here. The Hall effect is caused by electric currents in the degenerate electron gas in the crust. It changes the distribution of magnetic energy in a way that isn't linear. This creates magnetic hotspots where currents gather and decay more quickly. Because these spots heat the surface in different ways, many magnetars show pulsing X-ray emission as hot regions move across our line of sight. The cooler parts of the surface may stay that way, but the X-rays are mostly coming from the hot spots. This makes magnetars look hotter than they would if the heat was spread out evenly. Observations made with Chandra, XMMM Newton, and NICER make this interaction very clear. Some magnetars give off a steady amount of heat, which is a sign of long-term magnetic field breakdown. Others have outbursts where X-ray luminosities rise by 10-100 times because cracks in the crust send rapid heat into the outer layers. Then, over months or years, these blasts get smaller and smaller as the crust cools down. This shows us both how much heat the neutron star can hold and how well it can transfer heat. Magnetar cooling also probes exotic states of matter. At densities above nuclear saturation, neutrons may form superfluids, while protons form superconductors, altering both neutrino emission and heat transport. When neutrons pair into superfluid states, they release Cooper pair neutrinos during the transition, briefly accelerating cooling before superfluidity suppresses further neutrino losses. Observing such rapid cooling episodes in ordinary neutron stars, like the one seen in the Cassiopeia, a neutron star, has already provided evidence for neutron superfluidity in nature. Similar observations in magnetars could reveal how ultra-strong magnetic fields modify these phases. The catastrophic physics behind giant flares. When a magnetar erupts with a giant flare, the energy released in less than a second equals what our Sun emits over 100,000 years. That raw violence demands an explanation. Where does this energy hide for centuries? And what catastrophic trigger finally lets it all go at once? The leading suspect is the magnetar's magnetic field, wound and twisted over decades or centuries by processes deep inside the star. As the crust cools after birth, its solid lattice traps magnetic field lines anchored in the dense interior. But the interior doesn't stay still. Currents in the liquid core slowly rearrange field configurations through Hall drift and ambipolar diffusion, dragging anchored field lines through the crust like giant tectonic plates under relentless stress. For years, a magnetar's crust bends and flexes under rising magnetic pressure, holding firm like an elastic shell. But every material has its breaking point. The neutron-rich lattice that makes up the crust has an incredible shear strength, many orders of magnitude stronger than steel. Yet even it can't resist pressures that climb to around 10 to the 29th dynes per square centimeter, under fields stronger than 10 to the 15th Gauss. At some point, the magnetic tension overwhelms the crust's rigidity. The result is a violent starquake, as the crust suddenly fractures and magnetic footpoints shift by kilometers in just milliseconds. This movement twists the external magnetic field, forcing previously stable field lines into unstable configurations. Above the surface, these twisted fields store energy like overwound springs. When reconnection begins, field lines breaking and rejoining in new topologies, it accelerates particles to relativistic speeds, launches alpha waves through the magnetosphere, and unleashes trapped energy as gamma rays, X-rays, and relativistic outflows. The first gamma ray burst during a giant flare is probably caused by this fireball of magnetic reconnection in the inner magnetosphere. When temperatures rise above 1 billion kelvins, electron-positron pairs, photons, and plasma are held by magnetic loops that are closed. As this fireball grows, it sends out gamma rays and heats up the star's surface where magnetic loops are anchored. This creates hotspots that power the pulsing X-ray tail that lasts for hundreds of seconds. Meanwhile, seismic vibrations from the crustal fracture shake the entire star. Observations of quasi-periodic oscillations, QPOs, in flare tails flickering at tens to hundreds of hertz suggest torsional oscillation modes ringing through the crust, or coupled magneto-elastic waves involving both crust and core. These vibrations slowly damp as energy escapes into space as light, neutrinos, or gravitational waves. The December 27, 2004 giant flare from SGR 1806-20 shows just how catastrophic these events can be. For 0.2 of a second, it outshone every other source in the gamma-ray sky, becoming the brightest extrasolar object ever recorded. The initial spike unleashed more than 10 to the 46th ergs of energy, followed by a fading tail that pulsed with the magnetar's 7.56-second rotation and carried quasi-periodic oscillations at 18, 30, and 92 Hz. The blast was so powerful, it briefly ionized Earth's upper atmosphere, even though it erupted 50,000 light-years away. If it had been closer, the consequences could have been devastating. Where exactly the energy resides before the flare remains debated. Some models emphasize crustal energy storage, with magnetic fields stressing the solid lattice until mechanical failure triggers both crust cracking and magnetospheric reconnection. Others argue most energy sits in the external magnetosphere itself, slowly twisted by crustal motions, until reconnection triggers a global magnetic reconfiguration. Both reservoirs likely contribute. The crust supplies slow footpoint motions twisting field lines, while the magnetosphere stores the resulting magnetic tension until a critical threshold sparks runaway reconnection. This plasma briefly catches radiation, creating a pair of fireballs that are optically thick and surrounded by closed magnetic field lines. As the fireball spreads and magnetic pressure eases, radiation slowly leaks out, creating the long X-ray tail that is changed by the spin of the star. Modeling this phase in great detail helps us understand why flare tails last minutes instead of milliseconds, even though the original energy release happened almost instantly. Occasionally, giant flares may eject relativistic outflows or magnetized plasmoids into surrounding space, producing radio afterglows as they shock the interstellar medium. The 2004 flare from SGR 1806-20 launched an expanding radio nebula moving at 0.3 c, revealing bulk mass motions accompanying the electromagnetic outburst. Whether these outflows contribute to cosmic rays, fast radio bursts, or other high-energy phenomena remains under active study. Despite decades of observations, giant flares remain rare. Only three, 1979's March 5th event, 1998's August 27th event, and 2004's December 27th event, have been confirmed in our galaxy or its satellites, though extragalactic candidates appear in gamma-ray burst catalogues. Their rarity suggests either long magnetic energy buildup times or special conditions, perhaps field topology, age or internal temperature, required for catastrophic reconnection. X-ray polarimetry from XPE, gravitational wave monitoring from LIGO and its successors, and radio afterglow searches with SKA may soon be able to get multi-messenger data from the next giant flare. This data could show how magnetic energy is stored, how the crust breaks, how the magnetosphere reconnects, and how relativistic outflows happen all in one clear picture. Burst storms, avalanches in magnetic fields. When big flares go off, they make news because of how powerful they are. Burst storms, on the other hand, are events in which dozens or even hundreds of smaller bursts hit the X-ray sky for hours or days. Even though each burst has a lot less energy than a big flare, when looked at together, they show that magnetars can release magnetic stress not only through huge explosions, but also through a series of smaller events that move like an avalanche. These storms are like aftershocks from a big earthquake in the star's magnetic crust. They show us how magnetic fields store and release energy on a wide range of scales, from huge explosions to tiny cracks. A typical burst storm starts suddenly, breaking months or even years of silence. Without warning, the magnetar erupts with a flurry of soft gamma-ray repeater bursts, each lasting only fractions of a second, but releasing between 10 to the 38th and 10 to the 41st ergs of energy. At the height of the storm, bursts can fire off every few seconds, filling the sky with rapid flashes before slowly calming over the course of hours or days. In some cases, the sequence ends with a colossal giant flare. In others, it simply fades back into quiet, leaving the magnetar dormant once again. These storms first drew attention in March 1979, when SGR 0526, 66 in the Large Magellanic Cloud, produced dozens of bursts before and after the famous March 5th giant flare. Later storms from SGR 1900+14 in 1998 and SGR 1806-20 in 2004 showed similar patterns. Intense burst activity clustered in time, often preceding or following the most powerful flares ever recorded. What drives this behavior? The leading model invokes magnetic reconnection and crustal fracture cascades. As magnetic stress builds inside the star and its magnetosphere, small fractures or localized reconnection events may destabilize neighboring regions, triggering chains of energy release, much like earthquakes triggering aftershocks. Each burst represents a patch of magnetic field snapping into a lower energy configuration. Collectively, the sequence reflects an avalanche process in a system near critical instability. This idea is backed up by statistical studies of burst energies. A power law shows that small bursts of energy happen a lot, while large ones become exponentially less common. This is exactly what you'd expect from self-organized critical systems like earthquakes, solar flares, or sand piles falling apart under their own weight. The crust and magnetosphere are being pushed toward a critical point by magnetar magnetic fields that are slowly twisting due to internal motions. Any change, whether temperature, magnetic, or mechanical, can cause avalanches of reconnection on many scales. During burst storms, X-ray spectra often show thermal components around tens of keV, plus high-energy tails extending above 100 keV. These likely come from pair plasmas in the magnetosphere heated by reconnection, and from particles bombarding the stellar surface along magnetic field lines. Some bursts exhibit quasi-periodic oscillations, QPOs, in their tails, hinting at seismic vibrations coupling crustal motions to magnetospheric currents during the storm. Magnetar rotation also modulates burst storms. Because hotspots form near magnetic poles where field lines anchor, bursts cluster at specific rotational phases as the star spins, revealing magnetic footprints controlling where energy release concentrates. This explains why X-ray pulse profiles sometimes change dramatically after storms, as magnetic footpoints shift or new hot regions appear following crustal reconfiguration. Not every magnetar storm follows the same script. Some remain limited to modest bursts over a few days, while others escalate into giant flares that unleash 10 to the 44th to 10 to the 46th ergs in just seconds. What tips the balance between a storm that fizzles out and one that detonates into a global catastrophe is still a mystery. It may depend on the star's magnetic field topology, whether stresses remain localized or snap across global field structures, or on how the crust responds, with strength thresholds shifting depending on its temperature, composition, or age. The April 2001 storm from SGR 1900+14 captures this uncertainty. Over 3 days, the magnetar erupted in hundreds of bursts, peaking at one every few seconds, pouring out more than 10 to the 42nd ergs before calming. No giant flare followed, but X-ray afterglows lingered for weeks as the crust radiated away heat from the widespread activity. In contrast, the 2004 storm from SGR 1806-20 built up until it erupted in the most powerful giant flare ever observed, suggesting that in some cases, storms steadily load magnetic stresses until the magnetosphere reaches a breaking point and reconnects globally, igniting everything at once. Avalanche models are like solar flares, which happen when magnetic energy in the Sun's atmosphere is released through reconnection cascades and flare storms.